in this presentation, me and Cherry would like to introduce you big data mining concept, techniques, and discuss the opportunities and challenges of mining health big data. Also, we will share with you our practical experiences in working with big data analytics. Okay, you already know me, so Cherry, would you like to say a few words to the student before your presentation? Cherry.
Oh, hi everyone, I am Cherry, and it's a pleasure to come here to this workshop. So you'll hear about my presentation a little bit after lunch today, so it will be a really good opportunity. Nice to meet you all.
Okay, good. So let me start the presentation. Okay, so basically this presentation will include three main parts. The first part is my part, is to introduce the database, the big data mining concept technique, and discuss the opportunity and challenges. And after that, I will go to Cherry and to let her share with you her practical experience in working with data mining, and then we come back to my part to give the concluding remarks. And of course, we'll give you time, so probably 30 minutes, depending on how much time we have for your lunch. Okay. And as I said earlier, the presentation include three main parts, seven small parts: introduction, real-world use case, and project of big data mining in healthcare. And then I will show you some big data analytics challenges and potential solutions. Of course, this part is not only applied to healthcare. The techniques apply to all kinds of the big data sets. And overview of big data mining. This go to Cherry part research project as a real world examples. And future research directions I like to share with you for your future research. And then give concluding remarks. Okay. So there's a go-to introductions part. Healthcare is the most data-intensive industry in the world. And today, a variety of modern health information systems such as EHR, computerized physician order entries, picture archiving and communication system, clinical decision support system, and lab system have generated an unimaginably huge volume of patient data. And world digital healthcare data was estimated to be equal to 25 exabytes. And Hugh, who is the colleague of mine in Stanford, he also predicts that the global growth in healthcare data will be between 1.2 and 2.4 exabytes. I believe that not all of you have a computer science background, and probably you don't have the good sense on how much or how big 2.4 exabyte is. So I give you an idea. Okay, so if you print it out, okay, 2.4 exabyte equal to two multiple 10 power 12 phone books. If we assume each phone book is 4 cm. Okay, so it's equal to 105 rounds from Earth to Moon. We assume the distance between Earth and to Moon is 384 thousand kilometers. So you know how big it is, okay, of 2.4 exabyte. Okay, and Now you have the idea, big data is huge, it's very big, but actually many people talking about the big data as a misunderstanding. They say, oh, I have a million or billion record, then I have the big data set. I would say this is not the correct idea. It's a misunderstanding. Actually, data volume is not the only component of big data. Okay. So I would say big data is different from so-called big data set in that it is a collection of data so large, so complex, so distributed, and growing so fast. Or sometimes we call it 5V, volume, velocity, variety, 5Vs. And so it becomes very difficult to maintain and analyze it using commonly used database system, such as nowadays relational database, such as Oracle or MySQL, SQL Server, etc. Those kind of the traditional relational database. It's very, very difficult to store that. Okay. If we're talking about big data in healthcare, we need to know actually the human body can be seen as a source of big data, and the amount of healthcare data come from the human body exists is growing faster than ever and pose both an opportunity and challenge to the healthcare sectors. Imagine how many hospitals in the 1980s use EHR as digitalized healthcare systems to capture health data. And now you imagine how many hospitals without those kind of advanced healthcare IT system. Okay, so based on those advanced health IT systems or applications, all healthcare data was digitalized. Therefore, huge volumes and very heterogeneous of raw data was generated by a variety of health information systems, as I described in the previous slide, such as EHR, CPOE, PEC, CDSS, and lab system. And those systems are used in many distributed healthcare settings, such as hospitals, clinic, laboratories, and physician's office. And healthcare data is very, very different from big data in other disciplines, such as a social network or business transactional data system, in that it includes structured data, such as the EHR, and coded data, such as ICD, SNOMED CD code, or semi-structured data, such as data coming from HL7 message, and unstructured clinical notes, medical images such as MRI, X-rays, genetic data, and other type of data. So it is very different from other type or other disciplines of big data, such as data coming from Walmart transactional data. Huge, yes, I agree, but it's very structured, very unique. Okay, but healthcare data is very heterogeneous, structured, semi-structured, and unstructured data. So this is the main difference between big data in healthcare and big data in other disciplines, such as financial or business. Okay, so you may be curious about, yes, big data is it's important and interesting. But Alex, can you tell us if you can share with us some real-world use case and national level project? Yes, here I'd like to share with some real-world use case and or the leading project. Okay, but before this, I'd like to share with you the application of big data in healthcare. It can provide fresh insight into life science, and it can design interventions for disease treatment, and it enables personalized medicine or healthcare, and it can help to identify healthcare trends and reduce medical expenditure, prevent disease outbreaks, and improve government healthcare policies. Okay, makings. And if you want to know more practical example, here I provided a hyperlink to save time. I leave this for you. If you are interested in knowing more examples, you can go to this site and use a hyperlink to see details. But here I'd like to show you two real-world big data use case. The first example is Google flu. You will see the left-hand side diagram. This is a Google Flu Trends application. It's a novel internet-based influenza surveillance system, and a study collect 21 months. The period is between year 2009 Jan to 2010 October data at an urban academic hospital in Baltimore, Maryland, to access the correlation of city Google Flu Trends data to cases of influenza. And the study found that GFT is the acronym of Google Flu Trends, had high correlation values with number of positive flu test result. You can see this. If you look at the diagram, you can see the green line is a Google Flu Trend prediction, and the number of adult positive flu test is the red line. So you can see the pattern is very similar. Okay. So this is the real world application or use case using big data analytics method. And the second example is coming from using Twitter message. In this diagram, daily reported case data for all departments from the Haiti Ministry of Health, which is the, if you look at this is solid, a blue line, and the daily volume of primary health map alert, which is the, if you look at the dash red line, and the daily volume of Twitter post containing the word cholera, which is the dark green line, has similar patterns, but the Twitter data provide an earlier disease outbreak information, probably a week earlier than the real outbreak. So you can compare the blue line pattern and the dot green line. So it's the pattern is similar. This means the prediction is correct, but the data, you can see the data get is probably 1 week earlier than the actual outbreak. So this is the second real world application use case. Okay, and here is the Intermountain Healthcare, which is a Utah-based system of 22 hospitals and 185 health groups, and affiliated insurers use more than 90 million of EHR records to perform health outbreaks analysis. And this group use two main systems to predict and to do the big data analytics, which is outcomes minor and population minor. To save time, I don't want to read through those two systems. Okay, again, if you want to know more about this use case, you can use the hyperlink to go to the website to see detail of this use case. Of course, there are also many other real-world use cases around the world, such as the French hospital use trusted analytics platform to predict emergency department visits and hospital admission. Here is the hyperlink. When you get the slide, you can use the hyperlink to see the detail if you are interested in this use case. And the US Thibodeau regional health system applied big data analytics to help reducing the mortality rate through the improvement in stroke care delivery. Here is the hyperlink to see the data, to see the details of this use case. And in China, they apply big data techniques for COVID-19 prevention and control in China. Okay, this is a recent study work and use case. Okay, and again, if you want to know more other application use case, you can use the hyperlink here to see details of those other use case. Okay, now probably you want to know well, if there's a national level or top levels project for big data analytics or big data application project to healthcare. This is the UN Global Pulse program. Okay, regarding this project, UN Global Pulse is an initiative on big data and artificial intelligence established based on a recognition that digital data offer opportunities to gain a better understanding of changes in human well-being and to get real-time feedback on how well policies response are working. Again, I also provide hyperlink to let you go to the website to see detail or more information about this project. Okay, so this is UN Global Pulse. And the second national level project is called Precision Medicine Initiative Cohort Program, also called All of Us, which is an initiative announced in year 2015. And this project aims to collect genetic and health data from millions of volunteers and use big data analytics techniques to make advance in tailoring medical care to the individual. Okay, this example is called Big Data for Medical Analytics. It's the largest EU-funded initiative, okay, to transform the region's healthcare sectors by using state-of-art data techniques to achieve breakthrough productivity in the sector by reducing costs, improving patients' outcomes, and delivering a better access to healthcare facilities simultaneously. Okay, so this is a EU big data application project. Again, here is the hyperlink. You can see detail of this. Okay, and this project is called Big Data at Heart. This project launches in year 2017. Is a 5-year project of the Innovative Medicines Initiative, which is again a an EU consortium consisting of patient network, learned societies, SME, formal companies, and academia. And this project's ultimate goal is to develop a big data-driven transactional research platform of parallel scale and physician's solution in order to deliver clinical relevant disease and scaled insight from real-world evidence and insight-driven drug development and personalized medicine through the advanced analytics. Okay, so basically this is US EU based system using big data for healthcare applications. Okay, and this is a real world project I conducted a few years ago with Island Health in Vancouver Island. And because the Island Health, also Island Health Authority at Vancouver Island, before we call it VADA, is one of the 6 provincial health authority in DC, and the data warehouse at Island Health has 100 facts and 581 dimensions table, and compares a total of 10 billion record archived over a period of 15 years at that time when we do the research project. At that time, the table, the data size is about 10 billion record at that time. Probably now it's Diron, are you there? Can you add some comment how big it is now?
Yeah, I think it's 10 billion, but that's Island Health archived for 50 years.
Yeah,
and so some of it's legacy and the new Cerner Millennium product that stored the data. So, and it's, okay. I think it's about 10 terabytes in total.
Okay, yeah, Diron is one of the researchers at that time with me to conduct this project. So this is it's not a big level or national level project, but it's actual project. Okay, and the purpose of this project is to conduct a study to associate the Island Health admission, discharge, and translation data and the Kai discharge abstract database data to discover their associations. Okay, and one of the testing study question is that here clinician want to discover the correlation for elderly to see the association of those 2 data sets. Okay, so we run data mining algorithm on 4,416 core computer clusters. We call it West Grid. West Grid is a supercomputer, or sometimes we call it a computer cluster, to discover healthcare hidden patterns. And we use Hadoop MapReduce technique as a resource or workflow locators, and then use HBase as the non-relational database to store the testing data, and use the distributed database, sometimes we call it NoSQL, and Apache Phoenix, Spark, Drill as the analytic tool. And the purpose of this is to use the similar makeup data. Of course, the data structure is the same as the Island Health data, and then to test the big data analytics platform. So this is the real world application for big data analytics at the local level. Okay, now you have an idea how big data in healthcare applied in the local level or national level. Now, I'd like to introduce you the big data analytics, short of the BDA challenges. And if I can, I will show you or provide you some potential solution for each challenges. Okay, so big data are not usable until they can be aggregated and integrated into a method that computer can process to generate knowledge. And extracting useful knowledge from big data can be considered as a process pipeline that involves multiple distinct configuration stages, including data aggregations, data maintenance, data integration, data analysis, and pattern interpretation. And each stage faces several specific challenges. So from now on, I'd like to introduce you the challenges for each specific stage. Regarding data aggregation challenges, actually, big data research project involve multi-organization. It is very difficult to collect a real health big data from only one organization. Imagine the health data. Can you get the real big data in healthcare from one hospital or from one health authority? It's difficult because the data coming from different location, different healthcare setting. So big data research projects usually involve multiple organizations, different geographic locations, large numbers of researchers, and a variety of data types from different disciplines. However, given the wide range of data location, format, structures, semantics, and access policies, the data aggregation and integration become very complex and difficult, such as where can I or where do I find the data I need? Say I want to find a specific type of cancer data. How do I get the data? From Island Health, Jubilee, or General Hospital, or anywhere? You don't know. How do I retrieve the data? Is the data stored in Oracle database or the local access database? You don't know. And you don't know how to extract them to aggregate together for your study in your local site. What is the data structure and format? I will explain this later, use metadata examples. Different database or storage system use different data structure and format. It's very difficult to aggregate them together to become a uniform data format for analysis. Again, what are the data access, or sometimes we call regulations in terms of the privacy security policies? Different data healthcare big data holder has a different data access policies and security regulations you need to follow so that you can get the real data. Of course, there are many other challenges in this stage to get the data for your study. The second challenge for big data analytics is about data maintenance. Since big data involves a large collection of data sets, it is very, very difficult to efficiently store and maintain the data in a single hard drive using traditional data management systems such as a relational database. For example, use IBM SPSS to store the data or use the Oracle database. It's very difficult. Also, it's a heavy IT burden in terms of cost and time for small organization or lab. And furthermore, preserving data privacy in big data era is a major issue in any big data analytics project. So now, can you provide your idea? Do you know any solution or method to store 2.4 petabyte or exabyte data in a single storage space and can satisfy all my previous mentioned issues? Privacy, storage challenges. Do you have audience? Do you have any comment on this? How do you store this huge volume of data and can preserve privacy and security and has the capacity to ability to store the data? Do you have any comment on this? Do you have any potential solution for this?
What about cloud-based storage solutions?
Can you tell your name? You are smart, yes, and that's why I want. Yeah, nowadays, yeah, people talk. If you are interested in this, I several years published a paper in cloud computing. Yes, some researchers suggest to store the data in the cloud because the cloud provides a distributed ability to store the data, and cloud computing can provide security and privacy guarantees. Okay. Yes, that's right. Potential solution for big data analytics storage is cloud computing. But the issue is how to upload or download from cloud is a big issue because usually cloud was hosted by the cloud provider. Okay, and the cloud provider store your actual data in different locations. And if you upload or download 2.4 exabyte data, can you imagine how much time you need to upload or download it? Because the networking speed, probably if we want to download the 2.4 exabyte, say from West Grid, I guess you take several years. Okay. It's because the networking speed it's not enough to download it. You imagine now that the home network system, say Shaw, probably for 500 megabytes, and imagine use this speed of network. Can you download 2.4 exabytes data set to your local disk? Wow. This is challenging. Okay, so high-speed networking for big data analytics is also a big research direction. Okay, and also data privacy preservation is a major issue in BDA. Typical example is the HIPAA, Health Insurance Portability and Accountability Act, requires the removal of 18 types of identifier, including any information that could identify individual patients. So if we want to store the patient data in the big data era, you need to follow the HIPAA regulations. And this is also challenges. For example, you need to remove patient's identifier. And this is a challenge. For example, if you do big data analytics to find associations, and say you lost a patient's name or living area or say age, and then you are not sometimes you are not able to answer certain questions. For example, which areas get more rates of say liver cancers or breast cancer, or the patient's age range. Say female patient between 40 to 50 is more likely to get a breast cancer. Okay, if we don't have this kind of information. If we have enough time, I will use some real world example to show you the change of this, because the change coming from privacy regulations that forcibly remove some important or key data from the data set for analysis. Okay. And the third type of change is about data integration challenges. The integration process involves combining and transforming data into an appropriate format for analysis. Since big data in healthcare are unbelievably large, distributed, unstructured, and heterogeneous, the management of data integration over time is a big challenge. Particularly integrating unstructured data is a major challenge for BDA. Of course, not integrate unstructured data is a big issue, but for structured data integration also has many challenges. Okay, I give you one example, show you why structured data is also a big issue for big data integrations. Not only structured, semi-structured or unstructured data integration challenges. Okay, so here is the example. Okay, here is the data, a single data. Okay, can you tell me what P45 stands for, D stands for, LO stands for, or 47, S87 stands for? Can anyone answer me this? Can anyone, which smart student can answer me this? Wow, you are not able, right? This is the data. Okay, however, if I provide you this information, oh, you know, okay, P45 is the patient's ID or PHN. Okay, and D is the patient's first name, LO is the last name. This is a male patient, age is 47, and the symptom is a knee injury using ICD code, which is S87. This kind of information, we call it metadata. Okay, so this is structured data. All right. And look at this. This is a real data stored in the Stanford gene database. That database stored probably 1 million of the genetic genomics data. And this is real metadata. But can anyone tell me what does this mean? Extract protocol CH1, what does this stand for? You don't know. Okay, so look at here. Why I say integrate structured data is also a challenge. Say X hospital use patient's name to store patient's first name, and hospital Y use first name, last name, 2 column to store the data, and hospital X use sex, hospital Y use gender, hospital X use birthday, and hospital Y use DOB. How you expect computer understand sex equal to gender? Yeah, we know, we human being understand, but computer doesn't know. If we don't provide or extract exactly provide this information to your program. How do you know birthday is equal to DOB? And even diagnosis system or coding system, this data using SNOMED CD code to record abscess of food. However, hospital Y use ICD 10 code, which is L02.4. Okay, how can you integrate those two data together to become uniform data format. Yeah, you need to tell the integration system in advance. But how many code can be in the system to record patient's diagnosis information? Very difficult. Okay, so that's why I say even structured data integrations is also a big issues. Of course, this is out of the scope of today's topic. It's related to standardization of the healthcare data. Okay, and integrate unstructured or semi-structured data. It's a big issue. Okay, so now we go to data analysis challenges. For some analysis algorithm, the computing time increased dramatically, even with small amount of data growth. For example, in the case of patient network. Okay. Okay. Why this is the issue? Because for small amount, you can use ordinary computer to analyze it. Okay, and use some commonly use algorithm to analyze. A typical example is here. I use this data set include 4 columns. Okay. Use 8 columns to store the patient's data. Of course, this is far from real. This is make-up data. I just want to use this example to give you an idea why the data analysis algorithm is a big issue if you want to do the big data analytics. And then I use this data table structure to generate a different amount of data to test the same algorithm. Okay, and the study question is to list all diabetic patients with congestive heart failure complications who are younger than the average diabetic patient of the patient's home country in the world, because this data set store the patient's information and living countries. And then I design a PL-SQL, okay, to analyze this make-up data set to answer this study question. Okay, and this is the result. Okay, if I use the previous data structure to store, say, 100,000 record, use the algorithm, it takes probably 9 seconds. But if I use the data structure to generate 1 million record, then I use a Dell Inspiron 580 computer with a 3.2 gigahertz CPU. Okay, to analyze 10 million of row without index. You can see it takes about 190 seconds. So the algorithm I provide earlier here is a non-linear algorithm. It is exponential. So now, use this trend, this diagram. Can anyone tell me how much time this computer needs to analyze 10 billion? Here I say 10 billion, not a million. 10 billion. How much time use the algorithm? Okay, the answer I will provide to you later. Okay, so even for small data analysis, it could take several days or even months to obtain the result when data is very, very large. For example, 10 billion record or terabyte or exabyte. Okay, so say if I use the data set, say 10 billion, okay? And the starting question is that I want to find the average age of patients and percentage of female and male, and use a previous computer. I suppose it takes 1 second for the computer to obtain the report for a terabyte data record. It will take around 32 years to get the result of exabyte records. So you understand that the difference between the small set of data and a large set of data. So even the simple study question, this of course to answer this question is linear because you can sum up all the patient's age and divide the number of patients. So this is linear. It's different from previous group by example, which is exponential. So that's why I say even a small set of data, even a bigger simple algorithm to analyze huge volume of data, say terabyte, it takes time, too much time. Okay, so this is the big issue for analyze big data compared with old days analyze a big data set. Say you have the 10 million. Okay, yeah, use advanced computer to analyze the 10 million. It's not a big issue for using today's advanced computers. But if the data set is huge, say terabyte, so this is challenging. Okay, let me check. Okay, so we still have enough time to keep going. So what is the potential answers? So many recently published articles have suggested that parallelization of computing model can efficiently increase analysis performance and computerization intense problem. So the data set, the data mining task is a previous example. If the data set we distributed to say 10,000 computers or computer clusters, it only takes 1.16 days compared versus 30 years, right? If you use the algorithm to analyze the previous data set, okay, it takes 32 years. However, if you have computer clusters contain 10,000 cores, it only takes 1.16 days. So yeah, 1.16 days is acceptable, but 32 years is not acceptable to analyze the data, right? Okay, so the last issue for big data analytics is the BDA is of little value. If the decision maker do not understand the pattern it discovered. Unfortunately, given the complex nature of data analysis in big data, it is challenging to represent and interpret result in a form that is comprehensible to non-expert. I believe the audience here, most of you do not have the computer science background and you are a healthcare professional. Okay, but if I provide you the patent information about the confidence is the p-value is 0.005. What does this mean? Probably you don't know. If I provide the association rule of patents and provide you some value, probably it doesn't make too much sense to you. Okay, and also many people believe that bigger data always provide better information for decision making. Unfortunately, agile data science may not be able to protect us from inaccuracy, missing information, and false assumptions. Right? In computer science, we have a saying, garbage in, garbage out. If you analyze the data set, it's not accurate or not clear, then you get the wrong data set. No matter it's a data set contain 10 billion record or 2.4 exabyte, it doesn't provide any useful information to you if the data itself is not good enough. So now there's a term, say data quality is important for data mining or BDA. If you want to do BDA or data mining, you need to make sure your data or data quality is good. Okay. But anyway, the potential solution for this stage is that we can use some kind of the visualization tool, such as Tableau, infogram, or chart blocks, or draw wafers to provide a diagram to show to non-CS background people. Okay, to provide useful visible patterns to non-expert. Okay. Now we go to the fourth part, which is the main topic for today's presentation about big data mining. Before I introduce you some data mining techniques and concept, I want to show you some data analysis categories. Actually, the data analysis can divide to three main categories. One is called simple SQL query, or data cube analysis, or let me see. Go to, okay, we call it hold on, OIP. Okay, so let us repeat this concept. I try to categorize the data analysis to three parts or three types. One is called simple SQL query. For example, you query the database to find the average of patient's age. Okay, this is simple query. Or you want to find how many patients got through in Q4 in BC. Okay, of course, you can query the database. So this is called simple query. And OLAP is a more advanced analysis. We call it data cubing and dicing. Okay, and the third category is about advanced data mining. Okay, so this is the simple database query. Say this is a data set, and I want to find, okay, how many workers whose annual salary over than 10,000. Of course, you can query use this SQL command to query the database, and it get you three results. So this is very, very simple SQL query. This can easily perform using SQL commands for any type of relational database. Okay, and this is the advanced analysis type. We call it OLAP. Say I have the data set here to store the country. To simplify the explanation here, I use 4 provinces: Quebec, BC, Alberta, Ontario, and 4 diseases: cancer, heart attack, diabetic, flu, and 4 quarters, 1 year, to demo this. This means the data, say the database store the data divided to different categories. And then your study question is, how many citizens got flu on Q4 in BC? So this is your study question, right? Okay, so I try to use OIP to answer this question. First, I use the disease as a criterion. Okay, so this query will return you 16 data cube. Imagine each cube store the patient's information. Why I just get 16 cubes of data through this criterion? Because I just care about flu. So I don't need to care about diabetes, heart attack, or cancer. Those data are not the study data I need. So the first OIP stage to use disease as a criterion, and then I get the data set. And then the second step is to use area or province as a criterion, because the study question is to find the patients got flu in BC. So I don't need to care about data in Alberta or belong to Quebec or Ontario. So I get 4 data cubes, small cubes here, Q1, Q2, and to Q4. And again, come back to the study question, because the study questions is to find flu and Q4. Okay, so I use the third criterion, time. I get the data set. So you get the single data set cube. And this cube probably contain, say, 600 or 800 or 1,000 patients got flu, of course, in BC in Q4. So you get the answers through this kind of the OLAP analysis process. Okay, so this is called cubing and dicing process. So this is second type of analysis. Okay, so now we go to data mining process, which is a third type of analysis. Data mining is different from online analytical processing, OLAP, that focus on interactive analysis of data and typically provide extensive capacity for visualization and generate summary statistics. It is the process of automatically discover useful information in large data repository, particularly in data warehouse, just like I provided the example in the early slide. And the data mining process consists of major transform phases. Let me check the time. Okay, we still have the time because I promised to give you time to have your lunch from your Manitoba side. It's 12:30, and in Victoria time is 10:30. Okay, so I keep going. We still have 30 minutes to go. Okay, so as I described earlier, the data mining includes 4 main stages: problem definition, data pre-processing, pattern recognition, and the pattern validation. For problem definition, in this phase, data mining expert, business expert, or here we call it healthcare setting managers and domain experts work together to define the project objectives and the requirement from a healthcare quality improvement perspective. And the project objective is then translated into a data mining problem definition. So if we want to do data mining in healthcare, you need to clearly define what is your study question or problem. Quite often, people want to create a project for healthcare data mining, but people doesn't know exactly what the study we want to answer. Okay, so this is the main problem for data mining. You need to exactly know what you want to get the pattern from the data. So you need to know what is your study question. And then data pre-processing, as I introduced you earlier. The original raw data which are provided for data mining often need certain level of pre-processing before they can be input into a data mining algorithm. As I say, garbage in, garbage out. So you need to clean the data and do some kind of data pre-processing. So discard missing data, or clean the data, or fill out the missing data, etc. And the purpose of pre-processing is to transform the raw data into an appropriate format for data analysis. So excuse me for some water. Okay, and then go to the pattern recognition phase. This phase involves choosing the proper data mining algorithm to discover the patterns. Basically, these algorithms can be divided into 4 types. I will provide detailed information about those 4 types of data mining algorithms, include regressions, associations, clustering, and classifications. Okay, this is more computer science material than knowledge. I will introduce them later. And then go to pattern validation, or pattern, sometimes we call it the rules. This validation is the process of assessing how well the mining models perform against real data. There are several approaches for validating the patterns. For example, we can use a statistical method to determine whether there are problems in the data or in the model, or we can separate the data into training or testing data to test the accuracy of the patterns. Also, we can ask a domain expert to review or to validate the discovered mining patterns to determine whether the discovered pattern have meaning in the target business scenario. Here is called a healthcare scenario. So this is the data mining process. It's very similar to previous BDA, big data analytics. Okay, as I mentioned in previous slide, the data mining algorithm can be divided into 4 types: regressions, association, clustering, and classification. Okay, to give you a good idea of this, so firstly, I want to introduce you the first group of data mining algorithm. We call it regressions. Okay, regressions is kind of the prediction algorithm. In data mining, we call we call the supervised or unsupervised. Okay, so this is of course is a make up the data. I'll give you some more time to see the data. So which data is better? Can anyone tell me this? Use your common sense or instinct to tell me which data is better. There's a three doctors. Okay, and number of patients treated, and number of surviving patients, and the cost for the patient's care, and the length of stay in the hospitals. Can anyone answer me this? Yeah, just say something. Which data you prefer? Which doctor you prefer? If you are the hospital's manager or the directors, which doctor is the best or better?
Dr. A.
Oh, why you say so?
Well, number of surviving patients is more among all three.
But you see,
Yeah.
this doctor uses more hospitals resource from budget point of view, right?
Mm-hmm.
Well, if I can use the most expensive, the best drug or treatment, of course I can cure more patients, right?
Yeah.
So yeah, good. Thank you very much for your feedback or comment. Yes, use single factors or criterion to evaluate or judge a doctor. It's unfair. So here I use regressions. Before I go to the regressions equation, here, if you use, as you say, if we use effectiveness in terms of saving or surviving ratio, of course, Dr. A is the best. But if you consider the budget or in terms of cost, you can see Dr. B is better, right? Because the Dr. B use less hospital budget. Okay, and if we consider the length of stay, because length of stay is an important factors because the patient doesn't like to stay in the hospital too long, right? The patient need to work, or the hospital need to spend the resource to care the patient. So also the budget money, right? So if we consider length of stay, Dr. C is better. However, we need to consider factors. So we need to consider all factors for the doctor evaluations. So this time we use a regression analysis. Say we use a simple linear regression. So this is the outcome Y, and there's three factors: length of stay, cost, and the surviving rate. And we use the given data to answer the coefficients. I believe you get the high score of mathematics. You can easily use the given data to get the B0, B1, and E1, and then you get the coefficient for this regression equations. Okay, so this is the result. Use the provide data to answer this regression equation, and then you can use the equation to calculate the effectiveness, and we find, okay, Dr. C from three factors: surviving rate, cost, and the length of stay. Dr. C is below the average. So I would say consider those three factors. Dr. C is the best doctors. Okay, is this fair? You may say yes or no, but there, of course, there are other considerations. For example, surviving rate is the most important. Yeah, if you say so, then you can give the higher weight for the surviving rate, and then, of course, here you will get the different regression equations, and then you can use the regression equation, to predict other doctors' performance based on the doctors' three factors data. So this is called regression equation, called prediction. Okay, so this is the way we calculate the predicted data, use a regression equation. And the second category of data mining, we call it associations. This is a simple examples. Say there's a data set in the transactional database stored in the Walmart. Let me check the time. Okay, we still have time. 10. So there's 9 transactions stored in the Walmart database. Of course, this is far from real. Just a make of data to explain one of the association algorithm. I will introduce you later. So, okay. So this customer buy milk, beer, and diaper certain date, say in year 2011, July 23rd. Okay, this is a customer T100. Okay, and then can anyone tell me any patent you found through the given data set? Can you tell me any information or any patents? Just a glance at this simple data set.
Milk and beer are usually bought together.
Say again.
Milk and beer are usually purchased together.
Milk and beer. Okay. Wow. Okay. Because you find more milk, right? And beer. Okay. Yeah. You can say so. But this is not a systematic way to answer. You use your common sense, right? Okay. Okay. So I provide you the example using association. One of typical example algorithm, we call it a priori algorithm. This algorithm was proposed the researchers in year 1994, and the algorithm employs an iterative approach known as the level-wise search. We call it K item set to find the rules. Okay, and because this is not a data mining course, so I just keep quickly to introduce how this algorithm works. For this algorithm, there are two factors need to define. The support of an association pattern is the percentage of task relevant data transaction for which the pattern is true. Okay, so this is called support. What does this mean? If A item appear, also need to B item appear. In statistics, we call it union, A union B. Okay, so the support of an association pattern is the percentage of tasks relevant to data transaction for which the pattern is true. Okay, and the second data need for a priori algorithm is called confidence. So confidence is defined as the measure of certainty or trustworthiness associated with each discovered pattern. You don't need to care too much about how these two equation formed or to really understand how those two equations. But anyway, the a priori association algorithm need to have these two factors to find the final patterns. Okay, I use an example to show you this. I use a previous data set, right? Milk, beer. And then use the a priori algorithm. First, we did the minimum support count to be B. You need to set. And the confidence is 85. And then the algorithm scanned the database to count the number of customer purchase one items. Okay, so how many customer purchase one item? You can count. Milk, there is 6 customer purchase milk. You can count 1, 2, 3, 4, 5, 6, right? And 7 customer purchase beer, and only 2 customer purchase diapers. In here we call it nappies because of these UK terms. Okay, and then use this criterion. It passed the 1 items count, and then it go to 2 count part. So again, the problem count the number of customer purchase 2 items and compares the number with minimum support count. Because the milk bread are purchased by only 1 customer, so it is removed from the candidate 2 item set, because at the beginning we define the minimum account for the customer coming to our pattern is that the customer at least purchase 2 items. So if used this way, we get only 6 transactions item set. Okay, 4 customer purchase milk and beer together, and 2 customer purchases beer and diaper. We use this example and manual check the database. So okay, T100 purchases milk, purchase beer and diaper. Okay, this is okay. Beer and diaper. Okay, here. So T107 also purchase beer and diaper. If you scan the database, you will only find 2 transactions satisfy this condition. Okay, and the algorithm uses the same process to find candidate 3 item set. Okay, so there are 2 customer or 2 transactions purchase milk and beer and cheese. Similarly, 2 transactions purchase milk, beer, and diaper together. Okay, and then because there's no transaction over than 2 counts purchase 4 items together, so the algorithm stopped here. And then it go to the confidence. If you are the data mining project leader, you define the minimum confidence is 85. This means the count, okay, if it's over 85, then you believe this is the patterns you need. Okay, so you find only 3 patterns satisfy your conditions. Say if people or customer buy milk and diaper together, also purchase beer, and the confidence is 100%. This means if people buy milk and diaper, also buy beer. Okay, so this is a real case of a Walmart in the small town in the main USA. Okay, and the director or manager in this store find very interesting patterns. Okay, say if the people buy beer, also buy milk and diaper. Yeah. Find instance. Okay. Okay, here. The last patterns. If the customer buy diaper, also buy milk and beer. Wow. Why? This is the pattern, and the director find interesting patterns. Okay. So this is uncommon. So how do you interpret this, and how to apply the patterns? To save time, if we have time, then we can talk this and we can discuss this. Okay. And here is the example. I have published a paper to analyze the drug and drug reactions. We call it ADR detection. And this is the drug information. If people take B drug to help my pronunciation, the bad pronunciation, I call this drug B and drug L. Okay. And has side effect, reported side effect here. And if people take drug B, only 3 side effects. Okay, and then I use a priori algorithm to find the associations. And then we use minimal support count 3 and minimal confidence, and we find 5 patterns. Okay, according to the example, you find the patterns, and the interpretation is that if the patients take drug B and drug L together, will cause GI bleed, and the confidence is 100. So this is a real world application using association algorithm. Okay, so this is the interpretation. Use the patterns. Okay, then the third example for data mining is called clustering. And the clustering is an example to, a typical example is called k-mean clustering. Okay, and this algorithm is to use Euclidean distance to calculate the given data with the core. And the process to save time include 4 stages. If you use any software to develop this algorithm, it contains 4 stages, 4 steps, process stage. Okay, and here I give you an idea. Use visualizations. So you have the data set, okay, and you try to calculate, use Euclidean distance, and finally you find 4 clusters. Okay. Does this make sense to you? So if you at the beginning, if you look at the data set, it's not easy for you to find how many clusters that you have. But if you use a k-mean, you can easily find there's 4 clusters. Okay, so I stop this to come back to the slide. And the last data mining category is called classification. So KNN is one of the simplest and commonly used classification algorithm. And the algorithm assign object to the class that most of its nearest neighbors in the multi-dimensional feature space belong to. So the algorithm include 3 main steps. So this is the last group of data mining. We call it classification. So this is 3 main steps for this algorithm. So say you have a data set, and if you have a new data coming, and you want to find, oh, this data belong to which group? Okay, and then you can use KNN. Okay, so this is an example. Say there, the data, there are 3 groups. Okay, daisy, sunflower, and pansy. Okay, so now you have a new data coming. So this is the new data or new image. Can you tell me this is sunflower or daisy? If you check the color, it seems to sunflower. But you check the pattern, it's more likely to be the daisy. Am I right? So if you manually check this new image is a sunflower or daisy. Definitely, this is not a pansy, right? Okay. All right. Oh. Apologize for the issue of the slideshow. Okay, so this is an example to show you how you use algorithm KNN to class or to assign a new data to a group. We call it classification. And maybe you are confused. What is the difference between clustering and classification? Actually, both are similar, but the difference lies in the fact that clustering identifies similarities between objects, which is grouped according to those characters in common, and which different differentiate them from other group of objects, while classification uses a predefined class in which objects are assigned. To show for this concept is that for the classification is that you already have existing class, and then the newly come in object you want to assign to a specific exist class or group. However, customary is that you have a set of given data, but you want to try to categorize the data to few groups or several groups. So this is the main difference between those two algorithms. Okay, so now it's about time for you to do the lunch. So now we go to lunch time and take a short break. It's now it's a Victoria time 10:35. I have 5 minutes over. So there's comeback at 11 a.m. in Victoria time, and in Manitoba time is 1 p.m. And then after your lunch, then you go to Cherry's part to give the practical experience to show you her research project as a real world example.